So, good morning, everyone. So, I was given a problem regarding MATLAB for the subject CAE. The problem was given as, let me show you. The problem was given as to write a MATLAB code and to solve the transient 2D heat conduction equation using the FTCS method. And there are two conditions also given there. There we can use the square plate insulated boundaries on three sides and fixed temperature on and display time evolution of temperature field as a contour. So these two are the condition given to us. So let's start our MATLAB code for the problem. So we are writing the code here. So at first I will define the parameters. So I'm adding a comment percentage parameters and defining L equals to 1, which I have defined as the length of the square plate. So after defining this, the length of the square plate, so let's define another parameter as nx, which will define it as grid point. Nx, this is defined as grid points. So we are taking as nx equals to 26. We can take any imaginary number such as 20, 25, 30, 35, anything you can take. So I'm taking 26 here. So we will define this as percentage number of grid points, in x direction, in x x direction. X direction. So we have defined the nx, that is number of grid points. So now we have to define the grid points in y direction also. So we will define that as ny is equals to 25. So let's define this one as, let's add a comment here again, that is number of grid points in y direction. Y direction. So after defining ny, so we have taken the value of nx as 26 and ny is 25. I have taken any random values. So the nx is defined as number of grid point in x direction and ny is defined as number of grid point in y direction. So let's define the dx now. That is dx is equals to capital L. So we have defined dx equals to capital L divided by nx minus 1. So we're giving a bracket here, that is nx minus 1. So after defining this, giving inverted comma, let's define more properly, such as this is known as grid spacing in x. Grid spacing in x. So this is known as grid spacing in x, and similarly dy is equals to capital L slash ny minus 1 in bracket ny minus 1. So after giving the inverted comma here, so we'll define properly this as percentage grid spacing in y direction. Grid spacing in y direction or something. Okay, it is done here. Now we will define the value of thermal diffusivity. So we know that thermal diffusivity is denoted by alpha. So ALPHA, alpha is equals to 1e minus 4. We are taking the value of alpha as 1e minus 4. So after defining this, we will define this as thermal diffusivity. Thermal diffusivity. TRMAL thermal diffusivity. So up to here it is done. So let's check once that the screen recorder is on or not. The screen recorder is on here. So let's continue. So after defining thermal diffusivity, so we will define here alpha is equals to 1e minus 4. This is a random value we have taken for thermal diffusivity. Now let's define dt. dt is equals to 0.1. dt is equals to 0.1. We are taking the value of dt as 0.1. This is known as, if we defined it further by adding a comment, we will define it as the time step. As the time step. Time step. We will define as the time step. So after defining the time step, so let's define the final time output for which the control float will vary. So the final time output will be written as t underscore final, that is equals to, suppose for 30 seconds I am giving. So let's assume it for 30 seconds. So I will define this as percentage total simulation time. Total simulation time. So I have defined all the parameters here. Then let's add a comment. Let's initialize the temperature field first. So by adding initialize the temperature field. Initialize the temperature field. Initialize the temperature field. Adding this comment here. So T is equals to zeros. T is equals to zeros in bracket ny, comma, and x. Ny, comma, and x. Take inverted comma. Let's move to the next step. So we will have to define the value of t fixed here. So t fixed is equals to 100. T fixed equals to 100. Adding inverted comma. So we'll define this as percentage fixed temperature in one side. Okay, so we'll define this as fixed temperature at one side. Fixed temperature at one side. So after defining this, so we have initialized the temperature field here. So temperature field has been initialized. Now we have to apply the boundary conditions. So for applying the boundary conditions, so let's add a comment here that BOUNDARY boundary conditions. Boundary conditions. So T, we will define this as 1. Okay, so 1, it will give us T fixed. Plus T fixed. So we will define this as percentage fixed temperature at x equals to 0. This is the fixed temperature given at x equals to 0. Fixed temperature at x equals to 0. So this is the fixed temperature x equals to 0. So after this, I have to check my screen recorder after a while because it is giving some problem. So let's move to the MATLAB code. So after defining the fixed temperature here, so now we will, so fixed temperature is defined. So now we will apply time iteration here. So the time iteration we will define by adding a comment as time iteration, time iteration. Now adding the value of t is equals to 0 or t is equals to 0, writing figure, F-I-G-U-R-E. We are writing figure, then comma, then defining this as the figure for contour plot. So we'll write create a figure. So let's create a figure, for the contour plot, for the contour plot. So it has defined here. So we have defined here. Now we will use while loop. So using while loop, while t is less than small t final, t is less than small t final, then it will give t underscore new is equals to capital T is equals to capital T, adding inverted commas here. T new is equals to capital T. Then we will define these as percentage to initialize the new temperature field. So we will add a comment initialize new temperature field. So after adding this comment initialize new temperature field, we will add the FTCS scheme which is mentioned in the question. So we will add a comment percentage FTCS scheme for interior points. So let's write the code for this. So it will be for, we are using a for loop here again, for I is equals to 2 ny minus 1. For I equals to 2 ny minus 1. So again using the for loop, for j is equals to 2 nx minus 1. So we have defined for I as 2 ny minus 1, for j 2 nx minus 1. After defining these two values, we will write as t new bracket I comma j is equals to t, again giving bracket here, I comma j plus alpha, ALPHA plus alpha, which was the thermal diffusivity. So alpha star, adding a star here, alpha star, again dt star, alpha star dt star. Then by applying a bracket here and adding three dots. So we're ending this code. And after this, we'll add one more bracket and then we will start. So the recording is going on. So we have checked the recording. So let's begin to our new code. So adding bracket here. So we will write as capital T, again bracket, I comma j, I comma j plus 1, I comma j plus 1, I comma j plus 1. After that, minus 2, minus 2 star capital T, 2 star capital T. Then again adding bracket, capital T, I comma j minus 1. So I comma j minus 1. So I comma j minus 1. So let's give a space here, I comma j minus 1. So it is done, I comma j minus 1. Then after that, we'll give space slash tx square plus up to here it is done. Then again we have to define the value of t as t. Then again bracket inserted, I plus 1 comma j, we have to write I plus 1 comma j. Then after that, space minus 2 star capital T minus 2 star capital T. Then again bracket I comma j. So it is defined up to here, minus 2 star T I comma j. Then adding plus T plus T I comma j, I minus 1 comma j, I minus 1 comma j, I minus 1 comma j. Then double bracket, space bar slash, define this as dy square, the bracket is closed. Let's end the for loop here and end. So after ending the for loop here, we are noticing that something error has been already shown as we have used the while loop here, but we have not ended this yet. So we have just ended the for loop that we have used some equations here for defining the problem. So now let's put some values or add some comment such as insulated boundary conditions, boundary insulated boundary conditions as zero flux, that is zero flux. Let's check whether the recording is going on or not. So I guess the recording is going on. So let's check this for once. So the recording is going on properly. So let's continue to the code. So we have insulated boundary conditions for as zero flux. Now after that we have to insulate the value of du slash dy as du slash dn is equals to, so we have to add a comment first. So comment du slash dn is equals to 0 implies the gradient normal to the boundary is 0. So after ending the for loop, we have applied some comments here such as insulated boundary conditions at zero flux, and adding another comment as du by dn is equals to 0, that implies the gradient normal to the boundary is 0, and adding another comment such as percentage using a central difference approximation for the boundary nodes. So we have used a central difference approximation for the boundary nodes. So now applying another comment for top boundary, that is defined as y is equals to L. Y is equals to L. It will be T new bracket ny and x minus 1. So we have defined that equals to, again, T new giving bracket ny comma ny minus 1 comma T new ny minus 1 comma 2 and x minus 1. So we have assigned this value here as 2 and x minus 1, 2 and y minus 1. Okay, then for the right boundary, we have applied the condition for top boundary. Now for the right boundary, we will apply. So by applying it for the right boundary, RIGHT, adding the comment right boundary, we will define this as x equals to L. X is equals to L. So it is done here. So by adding the code as T new, adding bracket ny minus 1 comma and x. After defining this, we'll put equals and against T new, applying bracket ny minus 1 comma and x minus 1. So we have defined up to here. After that, now again adding a comment for the bottom boundary, because we are using a square plate. So For the square plate, the three sides are already closed, and from one side, the heat flow will occur. So the conditions for top boundary is given as y equals to L, and the conditions for the right boundary is given as x equals to L. And for the condition of bottom boundary, so I'm adding a comment, bottom boundary at y is equals to 0, at y equals to 0. So the code will be t new underscore new. Let's start the bracket here, 1 comma and x minus 1. This is 1, and for another one, that is equals to t underscore new, t underscore new, t underscore new. Let's start the bracket here, 2 comma 2 and x minus 1, applying semicolon. Now we have to apply the temperature field, or we have to update the temperature field. So these are the boundary conditions applied. Now we'll apply a comment that update the let's write it, update temperature field, update temperature field. So by updating the temperature field as t is equals to t underscore new, t new, and small t is equals to t plus dt. So assigning these values, next move to the next part. So we have updated the values of temperature field. Now we have to plot the contour for the temperature field. So let's add another comment such as plot, the temperature field. Right. So after adding this comment, plot the temperature field, we have to use some specifications or some features such as contour F. So before writing the code, I'm going to check my screen recorder. So the screen recorder is working properly. So let's continue to the code. So my code was contour F. Now I'm adding a bracket here, and I'm adding linspace, contour F, linspace. Then again another bracket such as adding 0, comma, capital L, comma, and X. Okay, where it is done. Then adding another linspace, adding a bracket as 0, comma, capital L, comma, and Y. So defining the linspace ny, we'll add a comma here, then we'll apply T, capital T, then again comma, we apply the value 20, again applying comma. Now we'll add the feature which is edge color, EDGE HCOLOR, edge color. So defining this, now we'll add another, that is none. So after applying this, we are adding the inverted comma and moving to the next line, that is color bar, COLORBAR, color bar. So color bar, then inverted commas, Then moving to the next line, now defining the title here. So title we'll start a bracket here, then another bracket, and we will write here in inverted commas temperature distribution. Temperature distribution. Temperature distribution at T is equals to at T is equals to we have to write here T is equals to NUM num to STR. Num to STR bracket it is small t. Okay, so then up to here bracket it is small t bracket close. We are giving here the commas. Then in inverted commas we are writing the S and the bracket goes such as it is closed. In heading the inverted comma, we move to the next line. So after defining the title, so we will add feature X label, X label, X label as X, and adding the X label as X. After adding the inverted commas, now we will set Y label as Y. After giving the inverted commas, let's move to the next line. Now we will add draw now. Draw now, adding inverted commas, and let's end the while loop here. So I have ended the while loop here. So this is my whole code for this problem. So I have to check the screen recorder once. So this is my screen recorder, and let's see. So it is seen that it is working. So I will try to run my code. So let's run my code here. So I can see that my code is running. This is the time variation and the temperature distribution at different interval of time. So here the time is varying. We can see that the variation of temperature with respect to time. The three sides of this square is closed, and from one side the heat has been blown. So we can see that the temperature is gradually varying or gradually decreasing or increasing. We can say the temperature is varying from one end to the another. Thank you.